Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. Last year, Elon started teasing his most ambitious project yet, which will involve xAI, SpaceX, and Tesla, space-based AI data centers to put us on the path to a Kardashev Type 2 civilization. Data centers in space might sound unlikely, but from both a technical and commercial perspective, they're possible. The question is, what needs to happen to bridge the gap between the possible and the real? Today I'll walk you through the challenge at 3 levels of technical depth. Surface level analysis based on what we see in space today, techno-economic modeling, and the key challenges from an engineering perspective. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. The simplest way to assess the technical and commercial feasibility of data centers in space is to look at the current state of space-based compute and extrapolate from there. SpaceX already has 10,000 Starlink satellites in orbit. Each of those satellites contains compute, laser-linked data transmission equipment, and several kilowatts of power and cooling equipment. And, of course, those satellites had to be put into orbit, which is currently still expensive. Despite that, Starlink is highly reliable and is now widely considered to be profitable. Data centers in space require the same basic ingredients as Starlink, but just in different ratios and at a much larger scale. That is, many people are talking about whether space-based compute is possible from a physics or engineering perspective, but ignoring the fact that we already have a basic proof in orbit today. With that in mind, let's move on to the next level of depth, which is techno-economic modeling for space-based compute. I've seen at least a dozen examples of techno-economic modeling online, but the 3 I found most impressive were by Mach 33, Pranav Myana, and Andrew McCalip. I'll link all 3 in the description because they're excellent, but I'm going to focus on Andrew McCalip's tool because it's probably the most accessible. As a side note, if you do access the links in the description, you'll find discrepancies between the calculators and analyses. For example, whereas Andrew McCalip estimates a baseline power cost of $22 per watt, Mach 33 estimates that it's $5 to $6 per watt. As Mach 33 explains on screen, the figures aren't actually in disagreement. Rather, it just comes down to how they've each isolated costs. With that in mind, let's run some numbers through Andrew's calculator to get an understanding of the current and future state economics of terrestrial versus orbital compute. Currently, powering a data center in orbit would cost about 10 times more than a terrestrial data center, so it's not yet viable. However, if any of the cost assumptions for terrestrial compute are changed, it has very little impact on the total cost per watt of terrestrial compute. That's because terrestrial power generation, logistics, and infrastructure are all highly developed industries, so there's very little opportunity for cost reductions. Scott Manley, for example, suggests that the falling cost of batteries will have an impact and somehow change the viability of space-based compute. It won't. Why? Because only 10% of the cost of a terrestrial data center is power. Even if the cost of batteries went to $0, there would still be generation costs to feed those batteries, meaning data center operators would only see an impact of around 3 to 4% with free batteries, which is a trifle in the face of the real challenge they're facing, which is scalability. Orbital compute costs are a different story. Even small changes in launch costs and hardware costs for power generation have a big impact on total cost per watt for orbital compute. In the case of launch costs, the cost target for Starship is $100 per kilogram to low Earth orbit, and longer term, they'd like to get that down to around $10 to $20 per kilogram. At around $100 per kilogram, the price of space-based compute is no longer 10 times more expensive than terrestrial compute, but more like 3 times more expensive. In the case of hardware costs for power generation, Starlink V1 satellites cost about $32 per watt, and they were first launched in 2019. Starlink V2 mini satellites cost about $22 per watt, and they were launched in 2023. That is, a cost reduction of about a third in 4 years. I'd be comfortable in assuming that trend continues with Wright's law as the deployment of satellites grows exponentially. If that's the case, we could see Starlink V3 in orbit by 2027 at a cost of $15 per watt. And by 2031, we could see the first orbital data center from SpaceX at a cost of $10 per watt. So if we assume orbital compute from Starlink would debut in 2031 with costs of $10 per watt for hardware and $100 per kilogram for launch costs, the total cost would only be about 40% more than terrestrial compute. Then, in another 4 years in 2035, it could reach cost parity with terrestrial compute, and would only get cheaper from there. However, within reason, even if space-based compute ends up being more expensive, as long as AI companies can turn a profit on that compute, they'll likely be willing to pay the cost premium. That's because even at the current small scale of the terrestrial AI ramp, we're seeing increasing public pushback on data centers and bottlenecks for power generation. It's better to have a lower profit margin on additional profits than no additional profits at all. That means scalability and speed of deployment are king in the AI race, and space-based compute can be scaled and deployed as quickly as it can be manufactured and launched into orbit. As a side note, why did Andrew's analysis focus on gas generation as the power source for terrestrial compute? I'm assuming it's because currently most tech companies are building their AI data center strategy around gas generation. That's because in many cases it's cheaper and faster to deploy than a large-scale solar and battery site. However, as I've stated in past videos, those advantages are likely to be temporary, and power generation for terrestrial data centers will likely shift to lower-cost solar and batteries in the future. But again, even if terrestrial power generation gets much cheaper, it won't change the more fundamental relationship between the cost of orbital and terrestrial compute, which is mostly dependent on launch costs. With the cost analysis out of the way, let's move on to the technical and engineering aspects of space-based compute, starting with the 3 primary advantages of putting data centers in space. First, satellites can be put in a sun-synchronous orbit that rides the dawn-dusk line that circles the planet, allowing them to collect 9 times more sunlight than on Earth's surface due to 24-hour sun exposure at a much higher average intensity thanks to the lack of atmosphere. The constant 24-hour flow of power would also mean that no batteries would be required. That combination of factors means space-based solar panels offer the lowest potential power cost available in the solar system. As a side note, if space-based compute is successful, the sun-synchronous orbit would eventually become full, and other orbits that do require batteries would need to be tapped into. That would increase costs, but it would also be deeper into the future when hardware costs would be lower, meaning those orbits and satellites would eventually become commercially viable. The second benefit of orbital compute is that space is an infinite heat sink, which dramatically reduces the need for cooling equipment and therefore costs. As Jensen Huang recently said, around 98% of the weight of an AI server rack is the cooling equipment. More on that in a moment. The third and final benefit of space-based compute is, as I mentioned earlier, scalability. Even without public pushback on data centers, there's only about 100 gigawatts of easily accessible power available on the U.S. grid, which will probably be tapped out within the next 5 years. Yes, I expect AI companies can and will start building off-grid, which would dramatically reduce the friction and therefore scaling restrictions to data center growth. But by comparison, building in space is the Wild West, because it wouldn't require buying land or dealing with neighbors. So long as there's government approval, SpaceX could just send up a steady stream of satellites, eventually reaching tens of millions, which would be hundreds of terawatts of compute. If you want to know more about the orbits those satellites could be placed in, I'll link an article in the description from Mach 33. With the advantages of space-based compute in mind, let's look at some of the engineering challenges. To be clear, this list is by no means intended to be comprehensive. The purpose here is to address the primary challenges and show that a lot of brilliant minds are out there solving the challenges, or have already. Starting with thermal management, there are 3 ways to transfer heat energy: conduction, convection, and radiation. Conduction is the transfer of energy through a solid. Convection is the transfer of energy through the movement of liquid or gas. And radiation is the transfer of energy by photons using electromagnetic radiation. On Earth, computer chips are cooled through conduction from the chip to the heat sink, which then transfers the heat energy to the environment by convection using air or liquid. In orbit, there's nothing to convect that heat energy to, so it has to be radiated into space primarily through infrared radiation. Many people have claimed that the radiators required to reject the huge amount of heat energy produced by data centers in space would be too large and expensive for space-based compute to be viable. That's incorrect. Those people are failing to take into account that radiative cooling capacity rises with temperature to the 4th power, that computer chips can run very hot, and the surface area that can be achieved per kilogram of radiator. Let's take a closer look. As Mach 33 points out here, the radiator temperature is set by how hot the computer stack can run. For example, modern data center GPUs tolerate 90 to 105 degrees Celsius before throttling, and industrial and military-grade chips can run at up to 125 degrees Celsius before throttling. That suggests space-optimized GPUs could achieve the same, potentially trading service life for smaller radiators and lower system mass. If we assume a 30-degree temperature drop from the chip junction to the radiator surface due to thermal resistance throughout the cooling system, a chip running at 110 degrees Celsius would correspond with a radiator temperature of about 80 degrees Celsius. Then, once the radiator operating temperature is chosen, the question changes from "can we reject heat in space?" to "what class of radiator are we building?", which can change the radiator mass by 5 times for the same thermal requirement. Obviously, the lighter the radiator, the cheaper it is to launch into space, so the key measure for radiators is areal density, or the kilograms of mass required for each square meter of radiator, and the lower the better. The radiators on the International Space Station have an areal density of 13.9 kilograms per meter squared, and NASA has developed radiator concepts that achieve as low as 2.1 kilograms per meter squared. Conventional radiators on satellites typically hover around 5 kilograms per meter squared. The graph on screen shows that at 5 kilograms per meter squared and 80 degrees Celsius, a 100 kilowatt space-based data center would require 1,009 kilograms of radiator mass. With that configuration, the radiator would only make up about 19% of the mass of the data center. The solar panels would make up 48% of the mass, and the body or bus of the satellite would make up 35% of the mass. What all this means is that radiative cooling for compute in space isn't some distant sci-fi type problem that dominates the challenge of space-based compute. Rather, it's an established technology that's available off the shelf and well understood by satellite engineers. The next challenge for space-based data centers is radiation. Terrestrial data centers are naturally shielded from charged particles from outer space thanks to the Earth's magnetic field and atmosphere. With orbital data centers, the higher you go, the less natural radiation shielding, which means an increased likelihood of temporary and permanent effects from radiation. By temporary effects, I mean particles striking transistors and flipping bits from 0 to 1 or vice versa, causing calculation errors known as radiation-induced bit flips. By permanent effects, I mean long-term radiation exposure that causes gradual damage to a chip's transistors. Those effects sound serious, but they're usually not, and they're both quite manageable depending on how deep into space the satellite is located. For example, Google's Project Suncatcher bombarded one of their Trillium chips with a 67 mega-electron-volt proton beam to simulate low Earth orbit. The most sensitive component, the memory, only began showing irregularities caused by permanent damage after it received nearly 3 times the expected 5-year radiation dose, and the chip kept working at up to 20 times the 5-year mission dose. That is, stock standard chips are surprisingly radiation hard for space applications. As for temporary effects, the radiation-induced bit flips were dealt with to an acceptable level with standard error-correcting code for inference-based applications. Inference compute is the type of compute used to respond to queries after the AI model has been trained and will likely make up over 90% of total AI compute in the future, which is one reason why Elon intends to focus his orbital compute ambitions on inference applications. For the training compute, on the other hand, the bit flips pose a greater challenge because higher precision is required, and for much longer time periods as compared to inference compute. That means each bit flip error would be less acceptable, and many more errors would accumulate for each computation run. And it's likely one reason why Elon intends to continue building data centers on Earth for training compute. Either way, with a chip designed for space applications, such as Tesla's AI-8 chip, the radiation hardness could be even greater than off-the-shelf chips and allow for higher orbits that receive greater radiation. That's important because it would open up more room for satellites in orbit and reduce the cost of the satellites because less structural reinforcement is needed at higher orbits. If you'd like to know more about that, I recommend reading Mach 33's article on the topic, which I'll link in the description. The next challenge for space-based data centers is maintenance. The solution here is pretty straightforward. The approach will be replace rather than repair. The useful life of GPUs for AI data centers is considered to be up to 6 years, but many fail before that and are replaced. For a space-based data center, that GPU wouldn't be replaced. It would just remain in the server rack. When enough GPUs have failed, and the satellite has reached the end of its useful life, it would be deorbited and replaced with another satellite. This is something that SpaceX already does. They replace an estimated 20% of their Starlink satellites per year. The last challenge of space-based compute worth addressing is the bandwidth and networking required between satellites and the downlink to Earth. For inference compute, bandwidth and networking are already a solved problem because the primary function of SpaceX's Starlink constellation is to move data around. Responding to AI queries would just be a matter of adding more compute to the satellite to process those queries on board. That's as opposed to what happens currently, where the query is beamed from the customer through the Starlink network in space to a terrestrial data center and then reverses that path back to the customer when the query is complete. For training compute, unlike inference compute, bandwidth and networking are not a solved problem. That's because whereas inference queries might use dozens of GPUs contained in one satellite, training AI models would involve hundreds of thousands of GPUs distributed amongst thousands of satellites. Not only that, the GPUs would have to be coherent, meaning that they'll need such high bandwidth between them that they effectively operate as one GPU. Google estimates the bandwidth requirement for space-based training compute would be around 10 terabits per second of aggregate bandwidth per link. How long will it take to achieve that? In response to Blue Origin's announcement that they'll achieve data speeds of 6 terabits per second by the end of 2027, Elon said that Starlink's laser links will far exceed 6 terabits per second. So maybe by 2030, they'll hit the necessary 10 terabits per second. However, even when they do solve the bandwidth problem, there will be other small engineering problems to solve for space-based training compute, like placing the training satellites as close as possible and keeping them in formation to improve latency and coherence. Besides bit flips, this is a second likely reason why Elon intends to keep building training compute on Earth and focusing the space efforts on inference compute. And while we're on the topic, the third reason why Elon is targeting inference compute for outer space is because Tesla's in-house AI chips are optimized for inference compute. Those chips should be much cheaper for SpaceX to purchase and vertically integrate around than chips from NVIDIA, which Elon's companies will continue to use for terrestrial AI training compute. Yes, they will eventually tackle space-based training compute, and it sounds like the eventual plan is to put Dojo training compute in space. But unless Elon's plans for terrestrial-based compute run into unexpected bottlenecks, I wouldn't expect the space-based training compute to happen until maybe the mid-2030s. For clarity, again, by space-based training compute, I'm specifically referring to coherent training compute. In a broad sense, inference compute for generating synthetic data will eventually make up most training compute, but it doesn't require coherence. With all the challenges in mind, when should we expect to see SpaceX start launching gigawatts of compute into space? For reference, a gigawatt of compute would take around 10,100 kilowatt satellites and would take hundreds of Starship launches. Even after about 15 years, Falcon 9 is only doing about 150 launches per year. So a fully and rapidly reusable Starship is critical to build out space-based compute in any reasonable time frame. If Starship starts carrying payloads this year, a prototype data center satellite could make a great, low-risk early payload. However, I think that's unlikely because they first need to start getting the V3 Starlink satellites in orbit that are going to pay for the development of the space-based compute business, and SpaceX will likely IPO in 2026, so they have a lot on their plate. If SpaceX orbital compute follows a similar deployment timeline to Starlink, and the first prototype AI data center satellite is launched in 2027, it would likely be at least another year after that before we see a full payload for those satellites launched in 2028. Then another year after that before the satellites hit volume production and we see regular launches that put up hundreds or thousands of satellites per year. But that's pure speculation on my part. A better indication might be to look at the development timeline of Tesla's AI-8 chip, which Elon has said will be out of this world. If the AI-5 chip hits mass production in 2027, and they intend on a yearly release cadence, then AI-8 would be hitting mass production in 2030 at the earliest. As a side note, as I was assembling this video, Elon posted on X that AI-7 instead of AI-8 is targeting space-based compute. However, I'd still keep my timeline at around 2030 for mass production of chips for space-based compute, because timelines seem to continue to slip for Tesla's AI chips. In summary, SpaceX's Starlink already runs thousands of satellites with onboard compute, power, cooling, and laser links in orbit, and it's reliable and profitable, which is a good indicator that the general concept of space-based compute is viable. Deeper techno-economic analysis shows that the primary gating factor for orbital data centers is launch costs. Yes, the cost per watt of space-based solar power will also be a key factor, but those costs will come down as more hardware is deployed. Finally, there are many critics saying that space-based compute is simply impossible from a technical perspective due to thermal management, radiation, maintenance, and networking challenges. Those claims are provably false with physics, engineering research, real-world examples, or all three. Space-based compute is only impossible or unprofitable without a fully and rapidly reusable launch vehicle. If Starship achieves that, SpaceX could be sitting on a $100 trillion opportunity. As always, please consider supporting the channel with the links in the description, which now also includes a referral link for Signature Solar. If you use that link to purchase home battery or solar equipment, it nets me a small percent-based credit, but that can add up on a large purchase and it really helps the channel. On that note, a special thanks to my YouTube members, ex-subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.